Today we want to start chapter 12 on multiple regression. And I think this is best done through examples, though today we're not going to do real life data. We're going to generate simulated data. We'll do the simulation in a spreadsheet, but then we're going to need Mathematica to do some matrix calculations for us. We're going to talk about matrices and vectors today and apply those ideas from linear algebra. On Thursday, we will get to seeing how things are done in R as well. But let's start by just writing down a new kind of model. You could call it a quadratic model for some data, or for a random variable y in terms of a non-random variable x. And even though it's going to be quadratic, even though we're going to have x to the second power, it's still actually going to fit under the rubric of linear regression. Linear regression. And you ask, how can that be if it's quadratic? This will still fits under what are called general linear models. Even though it's going to be a quadratic model. How can that be? We have to see how that works itself out. What I'm going to assume is that I've got a conditional random variable, y given x, whose mean is a quadratic function of x instead of a linear function of x. That's where the quadratic part is going to come into play. Some constant beta 0 plus some other constant beta 1 times x plus another constant beta 2 times x squared. So this is a quadratic model, the quadratic referring effectively to the fact that we've got x squared. The fact that it's general linear model, it still fits under that. I'm going to hint right now, is related to the fact that it's still linear in the parameters, the betas. It's still, still can't write the word still linear in the betas. The betas are not raised to like the second power or third power or square rooted or anything like that. We never really thought of things that way, but we could. So that's how the mean of y is assumed to depend on x. We're assuming really that the curve of regression is quadratic. We still might wonder how y given x is modeled overall. It's really the same way as with simple linear regression. Take the mean and add on a random error term, where that random error term we will again assume is normal with a mean of 0 and a certain variance, sigma squared. So it's still the same model here. The difference is in the model for mu. The difference is in the model for the curve of regression. Okay. So let's go ahead and assume, let's do a simulation in a spreadsheet. Let's go ahead and assume we know what the parameters are, beta 0, beta 1, beta 2, for the sake of simulation. So this is an example for simulation. Oh, let's assume beta 0 is 1, beta 1 is 2, and beta 2 is, let's say, -1/2. That's beta 0, that's beta 1, and that thing with the negative sign is beta 2. Okay, so I'm assuming I know what the betas are. I'd like to use a spreadsheet to generate some random data based on this model. I need to assume something about the variance. Let's also assume, so we are assuming here, that the variance is 1, so the standard deviation is 1 as well. Keeping things as simple as we can here. Let's now go to a spreadsheet, and we'll use Google Sheets so that we can ultimately use Excel Miner. But if you are in Excel on a PC, you should be able to get Excel Miner as well. That might automatically be in there. So pick some X values. I'll pick the X values to be pretty simple. How about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Picking 10 data points will make things simpler to think about as well. So those are the X values. Let's now make a column for mu. Mu y given X based on the particular population model that I wrote down. Based on this equation. So what do I need to do? I need to plug in that equation effectively and plug in these values for X. So 1 plus 2 times X minus 0.5 times X squared. Think about what's going to happen as I copy and paste this formula. I'm going to get points that are going to be exactly on a parabola, right? No randomness there. This is completely deterministic. Okay. These points are going to be exactly on a parabola. I think I'd like maybe the y values to not go so far negative. Let me actually change a parameter value. Let me change this to a 0.1 or negative 0.1. So they don't go so far negative. Maybe they'll still go negative, but maybe hopefully not so far. So I'll go back in here and change the equation as well. Copy and paste the new data. There we go. Okay, so maybe you have your spreadsheet open. I guess I didn't share this one with you. That's fine. You can be doing exactly what I'm doing. Again, there's what I typed and then copied and pasted, changing beta 1 to negative 0.1. And in fact, if you do that, then even by the time we reach 10, they're still positive. Yeah, if you plotted these points, they will be exactly on a parabola. No need for probability and statistics at all. Those are all exactly on a parabola. That's not really what I'm after then, because this is statistics. So what am I after? I'm after simulated y values. I'll just call them y. Well, okay, we should do e values first. Those random errors. E is normally distributed with a mean of 0 and a variance of sigma squared, where I'm assuming sigma squared is 1. Standard normal. We've done this before. Could do equals norm in rand 0,1. Right, rand will pick numbers between 0 and 1 with uniform probability according to a uniform distribution, continuous distribution. And then you plug that into norm in, you're going to get a z value effectively, a random z value that'll follow a standard normal distribution. Will be likely to be close to 0. almost guaranteed to be between -3 and 3 with 99.7% probability. It'd be very rare to get a number bigger than 3 or less than -3, though it could happen. Actually, maybe I should do E initial simulation, and then we'll have an E that represents frozen values. Not that you have to do that, but it's kind of nice to not have it change every single time. There we go. Almost all those values are in fact between -1 and 1. If you're doing this with me, you're going to get different values. I'll copy and paste this over with a paste special. Paste values only. And now they're fixed. Of course, once I did that, then these numbers changed. So these are going to be the E values that I'm going to use in this column. So now let's get the Y values. Look back at the model again. Use that equation. Y is mu plus E. This is a random variable form of the equation. Now we're using a non-random variable. We've got data here that's being simulated. But it's the same idea. Take the mu value plus E. Oops. Like that. Giving us then spread both above and below, not the regression line, but the regression curve, the regression parabola. And if I'm going to graph it, I'd want to graph column B along with column F. Let's see, I think I can do that. Is it control on a Mac? Nope, not control. It's command, I think. There we go. Command on a Mac is allowing me to highlight column B and column F here. Now insert chart. Change it to a scatter plot. Why did it not choose a scatter plot? There we go. With this particular simulation, in part because beta 2, I changed it to -0.1, pretty close to 0. That wouldn't be too far from being well fit by a linear model. If you pretend this is real data and you were looking at this initially, you'd probably try a linear model, right? It doesn't look too far from linear. I mean, yes, you can see a little bit of curvature to it, but most people would probably try to say, oh, maybe a linear model is not too bad, and then get a straight line maybe about like this. In fact, I could add the trend line. I'm not going to, but I could add the trend line and people would do that. But if you graph the residuals, you'd see a bit of a pattern to the residuals, and they'd be more likely to be positive in here and negative on the extremes, because this does have a bit of curvature to it because I used a quadratic model to generate it. But in real life, it's not so clear necessarily whether you should use a linear model or a quadratic model. Maybe you want to try both. Unless you have a good theoretical reason to try a quadratic model. If it seems reasonably linear, most people use the linear to start with. How do I find estimators now for beta 0, beta 1, and beta 2, 1, 2, and -0.1? Can it be done in a spreadsheet? Yeah, it can be. We can still use XL minor. Let me get rid of the plot now, just for sake of clarity. Yep, down to still go to linear regression still. First thing I always do is I click the labels box, then I make sure to include the label. The Y range is going to be here, column F, including the label in F1. And the X range is going to be column B, including the label in B1. Let's put the output, say, starting up here. Not going to do residuals and residual plots. And I'm realizing I'm making a mistake here. This will try to do a linear regression. Okay, let's get out of this. If I wanted to do a quadratic regression, there is something else I need to do on a spreadsheet. Let me insert a column here. And compute the values of x squared. If I want to use a quadratic model and get the spreadsheet to do it for me, to compute estimates for beta 0, beta 1, and beta 2, I need a column for the x squared values as well. And if you had real data, you'd still want to do that. If I didn't do that, it would assume it's trying to do an ordinary linear model. Go back to Excel minor. Linear regression. The Y range is now in column G, including the labels. The X range, okay, here's something else. Don't just highlight the X column, also highlight the X squared column. There we go. And if you typed it by hand, you'd want to type what you see there, B1:C11. Upper left corner is B1, lower right corner is C11. I need both if I really want this quadratic model. And yeah, let's not worry about residuals. Let's put the output starting in I1, say. Here we go. Okay. If it's going to work, there we go. Here's the output. Let's ignore everything up here. Let's just look down there and look, it's different than before. Now we've got 3 coefficients instead of just 2. There's still an intercept, but now effectively there's 2 slopes. Are they really slopes? Not really. They're coefficients. This one's very close to 2. Wow, I'm surprised it's so close to 2. That's not guaranteed to happen. Beta 1 was exactly 2. And these are the other coefficients. These are estimators for beta 0, beta 1, and beta 2. Remember, beta 0 was exactly 1. This is a little further away from 1 than this is to 2. Beta 1 was exactly 2. And beta 2 was exactly -0.1. This is pretty close to -0.1. If you did it with me, you got different numbers because you did a different simulation. Okay. So that's how you get your estimators. Let's go ahead and write those numbers down that I obtained in my simulation. In my simulation, you could write down whatever you got. My simulation. The observed value of what you might call capital B0, lowercase b0. It's about 0.4705. The idea is that's an estimate for beta 0. B1 is an estimate for beta 1. You can see is really close to 2. That's quite a coincidence that we were so close. And B2 is about negative 0.092288. That's an estimate for beta 2, the coefficient of x squared. There are confidence intervals for these things. Yes, and this one certainly contains the number 1, this one certainly contains the number 2, and this one certainly contains negative 0.1. So we are capturing the true parameter values for the population in this output. All right, what do we want to do now? So we did this, we did a quadratic model. What we want to do is we want to learn how to rewrite this in matrix form to relate it to linear algebra. Why? Because it makes the equations a lot easier to think about, that's why. Okay, it makes ultimately the normal equations a lot easier to think about and a lot easier to get technology to solve, actually, if you had to do some matrix operations to do the solving for you. How are these estimates solved for is what we're after. Just like with simple linear regression, let's do it with a bit of calculus. How are the regression coefficients found? Which reminds me, I still haven't explained where the word regression comes from. It's a historical thing. Not going to today. There's still SSE. But now we want to think of SSE as a function of 3 unknowns. Call them B0, B1, and B2. It's still least squares linear regression. We're still trying to minimize sum of squares of errors, meaning sum of squares of residuals. And you can still write it in this form. But now the residuals themselves look a little different. Because the model is different. We're assuming a quadratic model, B0 plus B1x plus B2x squared. And I should put subscripts on the x's, xi. I'm imagining data here. So I got data like my simulated data. X1 comma Y1, X2 comma Y2, X3 comma Y3, et cetera, et cetera. The B's are supposed to be estimates for the betas, right? Based on the data, what are the estimates that minimize SSE? I still need to use calculus. I still need to take partial derivatives. I can distribute the minus sign through here. Of these expressions here, of this thing, with respect to what? The x's, the y's, or the b's? What do I differentiate with respect to? This is a function of the b's. Differentiate with respect to the b's. The xi's and y's are fixed. Oh boy. Partial derivative of SSE with respect to B0, B1, and B2, and then set those derivatives equal to 0 and solve for B0, B1, and B2? Really? Yeah, really. We'll use the computer to help us. The derivative factors through the summation sign by linearity of differentiation. Differentiate that with respect to B0. The chain rule can be used, bring the 2 down. Multiply times the derivative of B0. Inside there is -1. I'm going to set that equal to 0. Partial derivative with respect to B1 is going to be something similar, except when you use the chain rule and differentiate the inside with respect to B1, you don't get an extra factor of -1, you get an extra factor of -xi. And then we'll set that partial derivative equal to 0. And take the partial with respect to B2. Something similar happens. But then the chain rule, when you differentiate the inside with respect to B2, you get a -xi². But we'll set that equal to 0. The 2's all cancel. They can go away. The negative signs can be brought through the parentheses, as well as, in this case, the xi's and the xi². All the negative signs in there will become positive signs, but then the yi's will have negative signs in front of them. The summation sign can be brought through each term, so I have a bunch of different summations. The summations involving the y's can be brought to the right with positive sign, because they'll have a negative sign here on the left from the negative signs being multiplied through. I'm trying to verbally say a bunch of steps that I'm going to skip by hand. To write the normal equations, a system of 3 equations and 3 unknowns, the unknowns being B0, B1, and B2. For the first equation, again, the 2's are all canceled. -1 times B0 is just a plain B0. I'll be adding B0 to itself n times. That'll be the same as n B0. That's the same as the sum of B0 added to itself n times. Right, I'm bringing the summation sign through as well. And again, the negative signs become positive signs. With the B1 term, the B1 can be factored out of the summation because it's a constant. It'll be B1 times the summation of the xi's, from the fact that there's an xi there. B2 can be factored out of the next one times the sum of the xi² coming from this one. And then again, on the right side, you really have, well, the sum involving the y's. -1 times yi is -yi. That negative sign can be brought in front of the summation, and then you can add it to both sides to swing it over to the right side without a negative sign. Get that. That's the first equation of the system of normal equations. Second equation is going to be pretty similar, except with each term, you're going to have an extra factor of xi. Which does mean for the B0 term, that I'm not going to get something so simple. I need a summation. B0 times the sum of the xi's. With the B1 term, I have an xi squared. That gets brought through. And with the B2 term, there's an xi cubed. Oh. And sorry, it's unavoidable. The y term also has an extra factor of x, and again is brought over to the other side as a positive. Sum of the products of xi times yi. Last one, it's going to be similar to what I just wrote down, except there's an extra factor of another power of x because of the xi squared. So in each summation, you up the power of x by 1. Which means for the last one, you have an xi to the 4th power. Here you have an xi squared. What fun. Solve the system of 3 equations and 3 unknowns. Do some linear algebra. You could try to put it in an augmented matrix and do row operations. You could even try to do it by hand. I would not recommend it. It's not going to typically be very nice. You should not typically expect B0, B1, and B2 to be very nice numbers. I mean, there will be, in examples like this, they will be rational numbers, but you typically would be writing them in decimal expansion, and they might have an infinite repeating decimal expansion when you try to solve for them. You could solve for them as fractions as well. So we'll solve this, not with a spreadsheet, but with Mathematica, and on Thursday we'll look at how to do it with R, matrix operations with R. Before we do that, let's note that this system of equations, as you know from linear algebra, could be written in matrix vector form. Remember, what's the unknowns? The unknowns are B0, B1, and B2. Make that be a column vector, B0, B1, B2. Those are the unknowns. That's your unknown vector that you want to solve for. The coefficients are the summations, and the upper left coefficient is just a plain n, simplifies to an n at least. The summations go inside here. Go ahead and take the time to write them all out like I'm doing. And notice this is not an arbitrary looking matrix. It's got a patterns to it. And one nice property you can say about it is that it is a symmetric matrix. These two numbers match. These two numbers match, and in fact, the middle one matches as well, though that's not necessary for a symmetric matrix. These two match. It's a symmetric matrix. Its transpose equals itself. You might remember from linear algebra that symmetric matrices are nice. And it turns out also that as long as you've got 2 data points for 2 different x values, this will be an invertible matrix as well. And on the right, I'd want to put these things. You should also remember from linear algebra that if indeed this is an invertible matrix, as it will be if you've got at least 2 data points with 2 different x values, you could solve for this unknown vector by multiplying on the left of both sides of this equation by the inverse matrix of this one, right? I call this matrix A. I'd want to multiply on the left by A inverse. Let's go ahead and compute these summations and plug these matrices into Mathematica and get Mathematica to solve it and confirm the answers that we got here. So I will need to add more to the spreadsheet. I'll need to add some more columns. It's okay. Insert some columns here. One column, say, for the values of x cubed. One column, say, for the values of x to the 4th power. And I can make these skinnier so it doesn't take up so much room here. How big will these numbers get? Well, 100 or 10 cubed will be 1,000. So, oops, forgot to cube it. Fourth power, x to the 4th power, 10 to the 4th power will be 10,000. What else do I need? I want to add up these summations as well. I need a column for products x times y and x squared times y. The y values are over here. Might make more sense to put those over here. So x times y and x squared times y. These are not going to be such nice numbers, though. X squared times y. Yeah, your right-hand side vector is not going to be such a nice vector. Not nice numbers. But the matrix, the 3x3 matrix, the numbers will be fairly nice. Add up these numbers. Equals SUM is what that is. I know that's kind of small for people in back. Adding up column B, B2 colon B11. Copy and paste this over. And then copy and paste it over here as well. Those are the numbers that need to go into the matrix and the right-hand side vector. Let's do that in Mathematica now. Let's go ahead and call the matrix A as we often do. You can click the matrix button on the basic math assistant or the writing assistant. It's a 2x2 matrix right there. You can make it become 3x3 by doing first control comma to add a column and then control return to add a row. N is 10, so that goes in the upper left corner. Don't forget about the N. Sum of the x's is 55. Sum of the x squareds is 385. Sum of the x cubes is 3025. And sum of the x to the fourth, you can see, is 25,333. That's A. Semicolon suppresses output. The right-hand side vector, should I call it Y? Okay, I'll call it Y. I can press the vector button and add a row, control return. Now I'm looking at the numbers in the spreadsheet that are highlighted, 79.1738971. Might as well keep as many digits as I can. 516.7041293 and 3,893.19172. Look good? Semicolon I can use again to suppress output if I like. And if I want to get the answer by a matrix multiplication, matrix form just formats the output as a column vector in this case. Do the inverse of A times Y. Matrix multiplication in Mathematica, you may recall, you need to do a period, not a star. So what should we get? We should get, hopefully, these numbers. 0.47, almost 2, and negative 0.09. Yep. Okay. You could solve it also with solve. Like this. Let's go ahead and do it. But the matrix approach will be helpful for us, and it's in the reading. There we go, same answer. What we want to do now is take this matrix approach and do something a little weird with it, but worthwhile. I'd like to write this matrix as a product of two other matrices. In fact, the product of the transpose of some matrix with the matrix itself. How? Well, it takes a little experimentation to realize this will work. But if you make a matrix, in this case, with n equal to 10 data points, it's going to be a 10 by 3 matrix. 10 rows because of 10 data points. Okay, I'll write it in abstract form first. The first column is going to be a bunch of ones, 10 ones, in fact. The second column is going to be a bunch of x1s. x11, x12, x13, x14, x15. I said these are a bunch of x1s. Why am I writing two subscripts? Although the last one is, I'll get the last one as x1n, where n is 10. If I wrote x110, it would get confusing because it looks like x110. x11 is the first observed value of the, you know what, okay, I made a mistake here. Cross this out. I'm thinking of a different situation. I'm thinking of multiple linear regression when I wrote that. Okay, let's go back. Let's write 10 ones. I don't need two subscripts. Just x1, x2, x3 through x10. You can put dots in there if you like. I'm purposely writing them all. There will be situations where we use two subscripts, but not now. That's going to be the second column of the matrix. Here's the last column of this 10 by 3 matrix. x1 squared, x2 squared, x3 squared, etc. The 10 by 3 matrix. 10 by 3 matrix. In general, it would be an n by 3 matrix when n is the number of data points. It's got a name. It's called the design matrix. 10 by 3 design matrix. What a beautiful name. Design matrix. Or maybe a little bit more officially, model specification matrix, which is not so beautiful. Model. Oh, I'm out of paper there. Model. I didn't realize I was writing on 2 pieces of paper. Model specification matrix. Design matrix is shorter and prettier. I think I'll usually say design matrix. What name should we give this matrix? A? No, we call it capital X. I guess that makes some sense because you got a bunch of X's in there. But remember, these X's are fixed numbers. This is a fixed matrix. This is not some matrix to solve for. You're not going to solve for X. These numbers are known. This is a known matrix. Okay, now I will use dots to save time. What would happen if I took the transpose of X and multiplied it times X itself? Well, first of all, can I do such a multiplication? X is a 10 by 3 matrix. 10 rows, 3 columns. Its transpose would be a 3 by 10 matrix. What's the transpose of a matrix like this? You got to swap the columns. Each columns become rows of the transpose. So the first column of X becomes the first row of its transpose. The second column of X becomes the second row of its transpose. The third column of X becomes the third row of its transpose. Yeah, I'll use some dots now to save some time. Now the first row has 10 ones. The second row has 10 X's. And the third row has 10 squared X values. That's getting multiplied by X. And I can do it. I can do the multiplication, you should remember from linear algebra, because these two numbers match. The number of columns of the matrix on the left matches the number of rows of the matrix on the right. So I can do this multiplication. And what kind of matrix do I get when I do the multiplication? There you look at the outside numbers. I'm going to get a 3 by 3 matrix. Dare I actually do the multiplication? I dare. Think about it with me here. It's actually not that hard. Upper left entry of the 3 by 3 matrix is going to be, do the first row there in the first column there, 1 times 1, plus 1 times 1, plus 1 times 1, plus etc. Add a bunch of ones. How many of them? 10 of them. N. N is 10. N is 10. I'm smiling. What goes in the middle spot of the first row? Do the dot product effectively of this row with the second column. 1 times x1 plus 1 times x2 plus 1 times x3 plus etc. through 1 times xn. Add up the xi's, in other words. Hey, we already did that in the spreadsheet. 55. 55. What about the next one? 1 times x1 squared plus 1 times x2 squared plus 1 times x3 squared, etc. We're adding up the xi squareds. $385. 385. No coincidence. It's going to keep going. It's a little trickier to think about, perhaps. For the first entry of the second row, look at the first row, the second row, first column, x1 times 1, x2 times 1, x3 times 1, etc. through x10 times 1. You're adding up the xi's. Yes, n is 10. I'm putting an n. For the middle entry of the second row, dot product of the second row here with the second column, x1 times x1 is x1 squared, x2 times x2 is x2 squared, etc. And I'm adding those all up. For the third entry of the second row, take the second row with the third column. x1 times x1 squared is x1 cubed. x2 times x2 squared is x2 cubed. I'm adding up the cubed values of the x's. And the pattern continues. We get the exact same matrices before. Also, if you compute x transpose times the vector I called y before, that vector, no, excuse me. I called that vector y before. That's not the vector I want here, but I am going to call it y. X transpose times y, where that y vector is the actual original y values from the data. Not the summations that I just showed you on the other sheet. Okay, now I'm putting an n here. I could have put a 10. The data y values what are you going to get? This is a 3 by 10 matrix when n is 10 times a 10 by 1 vector when n is 10. In general, would be a 3 by n matrix times an n by 1 vector. You can multiply them and you get a 3 by 1 vector. In fact, it's the other vector that I just showed you. Sum of the yi's for the first component, sum of xi times yi for the second component, and sum of xi squared times yi for the third. So what all this means is the normal equations can be written in, once you write down the design matrix, in a much more easy to remember form. The normal equations can be written as x transpose times x times the unknown b vector equals x transpose times y. And that's much easier to remember. And it applies to any situation where you're doing regression based on a general linear model, as long as you can figure out what the design matrix x capital X is. And you could also write down the solution of the normal equations in abstract form. You could say the b vector assuming x transpose x is invertible, which it will be if you've got at least 2 data points with different x values. B will be x transpose times x inverse times x transpose times y, right? All to get from here to here, I just multiplied on the left by the inverse matrix of x transpose times x. And by the way, this inverse here cannot be expanded in terms of inverses of x and x transpose individually, because x and x transpose are not even square matrices. So they don't even have inverses. You got to write it like this. There's your least squares solution. To the normal equations. Written in matrix vector form. B is an estimator vector, you could call it, of a vector, a parameter vector, whose components are the betas. You have parameters now that can be vectors, and estimators that can be vectors. All this kind of stuff can be done in other settings as well, including a different kind of model. Say mu is a function that's linear in 2 different variables. Say x1 and x2. That's a different model. This would be called a multiple regression model. As opposed to a quadratic multiple linear regression model. As opposed to a quadratic. You've got 2 separate independent variables explanatory variables if you prefer. The book typically calls them predictor variables. Not a single variable that's also being squared. Though you could call the plane x x1, and you could call x squared x2. If you did that, it would fit this pattern, though those variables would be tied together. They wouldn't be fully independent of each other. But the book sometimes does that. They talk about that. Bring in probability like this. Where, once again, E is assumed to be normally distributed with mean of 0 and variance of sigma squared. And once again, you can write down SSE as a function of 3 unknown parameters or unknown quantities that you'd want to solve for to minimize SSE. It does look a little different though, because you got B0, B1 x1 and a B2 x2 instead of a B1 x and a B2 x squared. Once again, you can minimize, you can solve for B0, B1, B2 based on some normal equations. Or what's going to be better for us is to write down a design matrix right away and write down the exact same equations in abstract form with the exact same abstract solution. And you can get Mathematica to solve it for you. You can also do it in a spreadsheet in a similar way that you did this case, except we'd have 2 separate variables, an x1 and an x2. But when you do the XL minor, you'd want to highlight both columns again, one for x1, one for x2. What is the design matrix in this case? The design matrix in this situation with n data points, The data points, by the way, are 3-dimensional. x1, comma, x2, comma, y1. And I should use a second subscript here, sorry. x11, x21, comma, y1. It's okay to just use one subscript with the y's. x12, x22, y2. x13, x23, y3, etc. The last one's going to be x1n, comma, y2n, comma, yn, or x2n, sorry. x2n, comma, yn. The first subscript corresponds to the variable name, x1 versus x2. The second subscript corresponds to the data point. The first data point, the second data point, the third data point. In the design matrix, it's going to be in this situation, it's going to be n by 3. N rows and 3 columns. You still have a bunch of ones in the first column. In the second column, you have the x1 values, x11, x12, x13 through x1n. And in the third column, you have the x2 values, x21, x22, x23 through x2n. The subscript labeling here is different than it typically is in linear algebra. Be careful. Usually the first subscript references the row number and the second subscript represents the column number. That doesn't happen here. The y vector is just going to be y1 through yn. But once again, to solve this, you still want to write down the normal equations, figure out what those are. And you can still solve it by using an inverse matrix, though of course, these things are going to be big enough, 3 by 3 in this case, because it's with these kinds of examples, 3 by 3 matrices here and an inverse. You'd want to use technology to actually solve it. Okay, so you should be able to solve it with technology, either with a spreadsheet or with Mathematica. Again, on Thursday, we will also look at R. Any questions? All this stuff also generalizes, as you'll read about, okay? You should be able to handle the generalization, and your X transpose X matrix in general could be even bigger than 3 by 3, 4 by 4, or 5 by 5, or 6 by 6. Depends on the model. Have a good day.